All right, today we're going to talk about electric circuits. You can see from the two illustrations here that we have some sort of wiring system that is attached to our light bulbs, which ideally is going to cause those light bulbs to turn on for us. So let's talk about the difference between these two images here. You may notice that they both have 3 light bulbs, but the light bulbs are not necessarily arranged the same. So both of these are illustrating electric circuits, but the difference in the arrangement is noteworthy, and we will talk about the differences between these two later on in the lesson. First, let's just talk about electric circuits in general. So it says here that we need to have a complete pathway in order for our electrons to move. So if you recall some basic vocabulary we've already addressed in this class, we have current, which is the rate of the flow of electrons, which means that our electrons have to be moving. So in order for us to have a current, in order for these electrons to move, they must be connected so that the positive and the negative end of our battery here in the picture, or just in general, our high and low voltage areas are connected so that those electrons then have a reason to move. So we talked about batteries as being a voltage source. So remember, voltage is what pushes or drives those electrons to move. There are direct currents, which are driven by batteries, where we have a designated positive and negative pole, which determines the direction that the electrons will be flowing through that system. And then we have alternating currents, where those poles flip, and so the direction will change. We will only be analyzing direct currents in our illustrations, where we know exactly what that movement is going to look like, and it will not change on us, all right? So we need to have a complete pathway involving our voltage source, which is a battery, a conductor, some sort of conductive material, which will typically be a wire for us. And then we need to have some sort of resistor or electrical device in order to keep our circuits safe. And I'll explain what that means with a little simulation in a moment. Let's go ahead and take a second and look at the illustration on this slide. So you can see that we have a battery. Our battery has a positive pole and a negative pole. So this is going to be what causes these electrons to move. You can read from the illustration that it says that we have one electron that's going to come out of the battery, and that one electron is going to cause all of those other electrons to move. So remember, the electrons are already present in the wire, so when this electron comes out of the battery, it is going to cause the electron in front of it to get a little bit of a push from it. Remember, like charges repel, so it's going to push that other electron forward. And basically, what ends up happening is a chain reaction, and all of these electrons, in order for that very first electron to move, all of the other electrons are going to have to move as well. They're going to make their way through the wire or through the circuit, and you see that they will return to our battery. Now, I want you to understand that we are following the conventional flow concept here as far as the direction, or what our rules are for determining the direction of our current flow. So according to the conventional flow, we have our electrons coming out of the positive end of the battery and returning into the negative end. So let's take a moment to look at a simulation here so we can get a better understanding of what's happening. Here I have a battery, and it is connected to an electric wire. However, there is currently no activity in the wire. So the simulator has the option for me to show the current, and I have that checked for us. But right now, it's not showing me anything because those electrons are not moving. The electrons are only going to move if we have a complete path, which right now we do not have a complete path. So what we need to do is take this wire, and we need to put it over here in order to complete that current. Now, if I put a little light bulb here, so I'm going to go ahead and start us off with a light bulb on our circuit. If I put a light bulb here and then I connect that final piece of wire so that we have what we call a closed circuit, or the path is 100% complete. Now you can see that my electrons are moving. We see that they are moving out of the positive end, flowing through the light bulb, continuing through the wire back to the negative end of the battery. If I were to take my light bulb and remove it, let's say that I didn't have a light bulb and I simply had a wire here, so it was just one big piece of wire. This will indeed complete the circuit, but you notice the color of my current has changed to a red, which is there to warn us. It says, warning, you have a short circuit detected. Now, a short circuit is a phrase that we use whenever we have a circuit where we are not flowing through a device. There is no resistor. And so this is dangerous. This is a problem because there is nothing restricting or limiting, slowing the flow of these electrons. And the end result of that is that this is going to generate a lot of heat, which can potentially ultimately start a fire, which is very, very dangerous. That's why the simulation changed it to red, because this is not a safe situation. With my device here, now those electrons are flowing safely through the wire. If I put it back where there is no device and I just have a direct current with no resistor on it, what I can do is I can take this fuse and I can place it on our circuit, and notice what happens is that the fuse actually breaks. So in order for us to have electricity flowing through the wire, we have to have a complete path. Now we want to have some sort of resistor present on the wire so that we don't end up with that excessive current that then causes a fire. Just a little side note, if there's a storm and you lose power and you guys simply go over to the little breaker box and you flip the switch on the breaker box to turn the electricity back on, that is evidence that the safety mechanism that the builders put in your home worked, okay? What happened here with our little fuse, you see that the fuse broke. That's because the current was so great that the fuse busted, which basically stopped or broke the circuit. So we open the circuit, the electrons no longer flow through that circuit. Now your house does not catch fire because of the excess current flowing through it. So although it may be a little bit of a nuisance to have to go and flip the switch, be grateful that the switch flipped. That meant that your circuit was receiving too much current and the breaker box did its job. Now, if you guys are having to go and flip that switch every time you have a storm, you need to get that checked out because that is not safe. But in general, that is the idea behind the fuses and the breaker boxes. That's so that they can open up that current and stop that, or open up the circuit and stop that current flow as needed for a safety mechanism. Now, it said on the slide that we could also have a switch. The switch is optional. So if I take a switch and I put it on our simulator, as long as the switch is, in this case, it flips to on, what that means is that the switch is currently down so that it is completing the circuit. If I flip my switch to the off position, then what you have done is you have changed the circuit. You have actually caused there to be a physical gap in the wiring, which does not allow those electrons to flow. So every time you flip the light switch in your room to turn the lights off and on, you are opening and closing the circuit. It's that simple, okay? So you have the switch closed or down, everything turns on because the electrons are moving, all right? Okay, so if we are looking at some diagrams of our circuits, there are some symbols that you will need to be aware of. We typically are using batteries as our voltage source. So a single battery is called a dry cell, but a lot of times we just say a battery. So this is our symbol for a battery. And on our battery symbol, you notice that these, or you may have noticed that these lines are two different lengths. That's because they represent the positive and negative terminals of our battery. Over here to the right, we have the symbol for our switch. And the switch right now is currently open. So whenever we have an open switch, whenever we have an open switch, that means that our circuit is incomplete. Okay, so this is an open circuit, so this is an incomplete circuit, meaning that we have a gap in that wiring or in that path. So anytime our circuit is open and we have that gap, this means that our device is going to be turned off. Now, if we wanted to illustrate that the circuit is closed, we could either take this wire and put that little line through it, which shows that we are pulling it down or closing it, or perhaps we have some sort of symbol where the switch would be open here, and then maybe they drew it so that the switch was closed, which you may not even recognize that a switch is present because it'll just look like it's part of the wire, right? And that's kind of the idea. Whenever we have our switch closed, this means that the conductive material is now completing the circuit. All of the parts are touching. So here we have a complete circuit or a complete path. And if that path is complete, then those electrons are going to move. We call that electricity. So then my device will be turned on. Next, we have this little symbol of the little zigzaggy jagged lines. This is going to represent our resistor. Now, this could actually be lots of different things in real life. It could be a light bulb, it could be just a resistor, it could be some other electric device. So just know that we use this generic symbol for all of those things that provide resistance. And then on the bottom right, you see just a straight line. This is going to represent our conductive material, which is typically just a wire for us in our circuits. These are some of the different types of circuits that we most commonly see. Now, series and parallel are both very basic, and we are going to discuss both of these types of circuits in great detail in this chapter. Combination circuits are a little bit more complex. You can see that it looks a little bit like series, a little bit like parallel, and that's basically what it is. It is a combination of the two types of wiring. At this time, I am not going to ask you to do anything with these combination circuits, but I did want to show it to you so that you have some exposure to it, and we will discuss this as needed in the future.